Hello and good evening, dear students, and welcome to my YouTube channel. We are moving on towards multivariable calculus 2 topics, and we are going to start with videos on surface integrals today. Prior to that, let us talk about scalar fields and vector fields. So, a scalar field, a function f from Rn to R, where n is greater than or equal to 1 and a natural number, is said to be a scalar field. So for example, we can take say f from R3 to R defined by f of x, y, z is equal to x into y into z. So if I take a vector in R3, let's say I take 1, comma 2, comma 3 in R3, then f of 1, 2, 3 is going to be 1 times 2 times 3, that's 6. So a scalar field is going to return us an image which is going to be a real number, while on the other hand we have a vector field. It is a function f bar from Rn to Rm, where n could be greater than equal to 1 while m has to be strictly greater than 1, and such a function is said to be a vector field. So for an example, let us take f bar from R3 to R2 defined by f bar of x, y, z is equal to x plus y plus z. So again, if I were to find out what is f bar of 1, 2, 3, this is going to be the first coordinate is x plus y, and in our case that is 1 plus 2. So we'll have 3 followed by y plus z. So that's going to be 2 plus 3, which is 5. So as you can see, a vector field returns us a vector in R2. Now we will be focusing on surface integrals of scalar field and vector field across this video. Now again, we got to talk about surfaces. So let's introduce us what surfaces in R3 are. Let us consider a two variable function. So let me define f from R2 to R. So we have taken a scalar field, and let me say f of x comma y gives us x square plus y square. We can also rewrite the same function as z is equal to x square plus y square. And as we know that every function has a graph, the graph of this function is going to be in R3. Let us see how the graph of this equation looks like. So if this happens to be our xyz space, then z equal to x square plus y square gives us a paraboloid. It's a paraboloid which opens upward or is oriented upwards, and it will be infinite since we have not yet defined the domain of the function. So it's quite easy to understand that a function in two variables, or more particularly a scalar field in two variables, gives us a surface in R3. And that's what we are going to look out at. So if we talk about surface integrals of functions, so in that case we are going to take the domain of these functions as surfaces in R3. So you are familiar with one variable integration wherein we integrate a function from a to b. So in that case, we have the interval to be a fixed length interval on the real line. And likewise, if we talk about the double integral, so for double integral, we have a region of integration, and that region of integration is very well placed in your xy plane. So in this case, this is your region R, and it is contained in R2. While when we move on to surface integrals, we are no longer looking out for such surfaces. Though this is a surface but it is planar, we will be more generally focusing on surfaces which are going to be formed in R3. And as a requirement of surface integral, we need to know how can we parameterize these surfaces, because that is involved in the calculation of surface integrals of both scalar fields as well as vector fields. So let me give you examples of a couple of surfaces, how we can parameterize them. So let's say S is the surface of the paraboloid So let's take z is equal to x square plus y square, where x square plus y square is less than equal to 4. So in this case, if we plot the graph is going to be like this. Now, if you will see that x square plus y square less than equal to 4 gives us the domain. So the domain is in the xy plane and it's an oval and it's a circle of radius 2 lying flat in the xy plane. And over this, we are going to consider the graph. I will have a paraboloid which will be like this. So this is what we have as the surface. So the surface is this curved part. So this is the front portion, and of course this is the portion which is not right in front, it is on the hind side. The very first thing which we will be doing for surfaces R is we are going to parameterize them. So we will say that let gamma be the parameterization of S. So by this we mean that we are going to define gamma as a function in R2, and it will be giving us the entire surface in R3. So in this case, it is easy to say that gamma of x comma y can be evaluated as x, y, and we are going to have here z. But since we know that the equation of this function is z equals x square plus y square, we could replace this as follows. So over here, the domain is going to be T, and that is the collection of all ordered pairs x, y, where x square plus y square is less than or equal to 4. So this is a way to parameterize the surface S. Alternatively, since it's using the equation x square plus y square, we could think of using the cylindrical coordinates, that is r, theta, and z. So if we take help of the cylindrical coordinate system, so in that case, we could parameterize the surface as gamma from R2 to R3, and we'll say gamma is a function of r and theta. Now in the cylindrical coordinates, x takes the value as r cos theta, y takes the value as r sin theta, and since we have z replaced by x square plus y square, and we know that in cylindrical coordinates x square plus y square gives us r square, and we can say that where the parameters r comma theta, they belong to T, and T will be the domain or the range for r and theta. So since if we look up at this surface S, if we look up at this surface S from the positive z axis, so in that case, what we are going to experience is we will be having the xy plane lying flat down, and on that we will have a circle, and on that we will have a circle whose radius is going to be 2 centimeter or 2 units. Okay, so for the range of r, we could say that r lies between 0 and 2, while theta, since it's a complete circle that we see from the top, we can say that theta lies between 0 comma 2 pi. We could use the semi-open interval for 2 pi. This is the domain. So again, gamma parameterizes the same surface S, as in both the cases it is going to be same. Now let's take another example and look out for the parameterization for it. So we have got S to be the surface of the cylinder, x square plus y square equal to 9, and this cylinder runs between z equals 0 up to z equals 3. So again, we first got to plot. So for the plotting part, let us have the frames. So we have the x, y, and the z plane, z space. So this is your x, y, and z. Now we have the cylinder of radius 3, and since you can see that the z variable is missing in the equation of the cylinder, So your cylinder runs across the z-axis. By that we mean that we'll have a cylinder, which moves indefinitely like this. So let us plot it nicely. So we'll have a circular base over here, and this is the behind part. And the radius of this circular base, as per the equation, is 3. And on this runs our cylinder vertically upwards. So basically, you have a circle of radius 3, and you keep on stacking multiple copies of it on top of the other and let it move along the z direction. So this is what we have. So now please note that your cylinder is made up of three surfaces, technically speaking. So one is the top flat surface which we have, and then the other one is the bottom surface, again which is a flat one, and then the next one is this curved part, of which the cylinder is made up of. So in this case, we are looking out for the curved part, since they have very clearly mentioned that S is the surface of the cylinder. So the cylinder is the curved part, and we'll not be looking out at the two flat circles which are the bottom and the top of this. And also, since it is an indefinite circle, now if you look further, we got to restrict the domain, we got to restrict our surface. So we are given that you need to focus between z equal to 0 and z equal to 3. Now we are very well aware that z equal to 3 is nothing but the xy plane. So it means like the floor of this so xy plane, it will be over here. So this is one part where our cylinder gets cut. So the lower part is not there. So I'll use a red. So this is not there. So we have a bound on the cylinder towards the lower side. And then also on the top, we can move up to z equal to 3. So z equal to 3, let's say we have to go 3 units above. So again, this will be a plane parallel to the xy plane and 3 units above. So let's say this is 1, 2, and 3 units above. So we got to cut the cylinder right across here. And what we will be getting is we'll get another flat portion which lies exactly over here. So we don't have an indefinite cylinder. We have a cylinder which is finite. The radius of the cylinder is 3. And the cylinder height is also 3 units, since it's from z equal to 0 up to z equal to 3. Now again, let's talk about the parameterization of this part. So to parameterize this, we will say that let gamma from R2 to R3 be the parameterization of S. So for this case, since we do not have Z being directly involved in the surface equations, which is given by this, so we'll not have the Cartesian parameterization. We'll switch to the cylindrical coordinate system. So again, in cylindrical coordinate system, we have that the two variables are r and theta. So I will say that x is equal to r cos theta. Now since the surface has a fixed radius, every point you take, so if I take this point, so this point is 3 units away from the origin or the z axis. So in this case, your x will be 3 cos theta instead of r cos theta, and likewise y is going to be 3 sin theta. And for z, now as you see that the z variable is not fixed, so if I move the points up and down, so the z values are going to get changed. So we'll say that z is equal to z in this case. So in this case, the parameterization depends on two parameters. One is theta and the other one is z. So we'll have the x coordinate to be 3 cos theta, y to be 3 sin theta, and while z remains z. And we got to give the domain as well. So we'll say where theta comma z belongs to t, where theta, again for theta part, we got to look for the projection. So if I again happen to stand on top of the positive z axis and look at the projection downwards, so I will see a circle whose radius is going to be 3. Just a quick heads up over here, I will not see a disk. I'm going to see a circle, a ring shaped structure whose radius is going to be 3, and it is centered at the origin. So theta will range between 0 up to 2 pi, And for the z, you have the limits set up between z equal to 0 up to z equal to 3. So this is going to be Cartesian product with 0 comma 3 closed interval. So that's the parameterization which we are going to get. Now let's quickly take up surface integrals of scalar field and vector fields, one problem from both. So this is one of the questions from practical 5, and it is about evaluation of surface integrals of scalar field f over s. We will be trying and solve question number 3. The practical sheet is available on the TYBSC page of my website, which for the link you can get into the description, and also you can head to the channel description. So we have got f of xyz is x square plus y square, and s is the surface of the paraboloid x square plus y square equals to 2 minus z above the xy plane. So we'll be beginning with how does the surface looks like first. So as you can see, the equation of the paraboloid given to us is this. So firstly, we will be looking at what does x square plus y square equals to z looks like. So x square plus y square equal to z looks like this. A paraboloid that is at the fixed at the vertex and oriented upwards. Now, if I happen to reverse the signature on z, so let me say x square plus y square equals to minus z. So in that case, the paraboloid inverts itself and gets oriented downwards, still touching the xy plane or at the origin. And for the last part, if the equation is changed like this, you add a 2 to the z variable. So in that case, this particular paraboloid needs to be shifted 2 units above. So it will be looking like this. So that's our paraboloid. So I'll be plotting it right now. So we have got the surface S given by the equation x square plus y square is equal to 2 minus z. Now also notice that it is said that the paraboloid is the surface of the paraboloid needs to be considered only above the xy plane. So of course, since it could go down as well, we are not really looking out at that part which is below the xy plane. So we have a base of this paraboloid which is this. Now again, you got to figure out what is the surface. So very clearly they have said S is the surface of the paraboloid. So the yellowish part which I have shaded right now, that is not the surface, and the surface of our consideration is going to be this. So the part which makes the paraboloid. So this is the surface of the paraboloid, and we could use the parameterization in the form of say cylindrical coordinates. So to begin with the solution, I will say let S equals gamma of t, where gamma is, we'll decide the variable. Now if you will look out that x square plus y square equals 2 minus z, so that is quite nicely done for making the use of cylindrical coordinates. So I will say it is x coordinate is going to be r cos theta, the y coordinate could be r sin theta, and then we need z also. So I cannot keep z as z because that makes 3 parameters, and surfaces always have only 2 parameters. So of course my parameters in this case are r comma theta. So for the z part, I'm going to use the equation of the surface. So from the equation of the surface, I get that z is equal to 2 minus x square plus y square. And in cylindrical coordinates, x square plus y square is r square. So I get that z is equal to 2 minus r square. So that would be my third ordinate. Okay, so we have got the parameterization. Then we got to tell what is the domain. So where r theta belongs to t, t will give us the range of r as well as theta for both the parameters. Now for that, again we got to stand on the top of the z axis on the positive side and look down. So if I look down, then I will be seeing this yellow base, which is the projection on the xy plane, and that particular base will be, the largest radius will be this one. So to find out what is the radius of this, it is the intersection of your surface x square plus y square equal to minus z with the z equal to 0 or the xy plane. So that means I got to substitute z equal to 0 in this equation. In another way, we are trying to solve these two equations simultaneously to get the solution. So if I substitute, I get the equation to be x square plus y square equals 2. So the surface which you are going to see will be having radius root 2. So the range for r is going to be from 0 to root 2, and since we see a complete circle, it is going to be 0 comma 2 pi, the range for theta. So we have got the domain of our parameters. Now moving on to the solution part. So the formula for surface integral of a scalar field over S, it is evaluated as double integral over T. So please note that there is no symbolic differentiation between how we can express a surface integral and double integral. So while saying, I will always say for the surface integral, this is the surface integral, while the integral that I'm going to currently write down on the right side is double integral. So the surface integral of f over s is evaluated as the double integral of t, and the integrand is made up of f applied on the parameterization, that is f of gamma r theta, multiplied by the norm of gamma r cross gamma theta, and then your parameters dr d theta. So this component is also known as the fundamental vector product or the normal to the surface. So as you can see, we need a couple of more things before we can head straight to the evaluation part. So we already have got what is the parameterization. Now we need to find out the normal or the fundamental vector product. So for that I need gamma partial derivative with r, and as you can see the first ordinate is r cos theta. So if I differentiate that with respect to r, I'll get cos theta. The second ordinate is r sine theta, so that gives us sine theta. And lastly, it's 2 minus r square, so that would be negative 2r. And likewise, if I go for gamma partial derivative with respect to theta, so that's going to be minus r sine theta, r cos theta, and 0. So for the fundamental vector product, we need to take the cross product or the vector product of these two partial derivative components. So it's evaluated as I hat, j hat, k hat. For the second row, we are going to take the first vector, which is gamma r. So it's going to be cos theta, sine theta minus 2r. And for the third row, we are going to the second vector, that's gamma partial derivative with theta, and that's negative r sine theta, r cos theta, and 0. So for the I component, we will have 2r square cos theta, then negative j. For the j component, we will have negative 2r square sine theta, and lastly, we'll have plus k. For that, we will have r cos square theta plus r sine square theta, so that reduces to k r. And this is as simple as 2r square cos theta. Then we could adjust the negative sign for the y ordinate, so that's 2r square sine theta and then r. So this is the normal or the fundamental vector product. So if you look back at the formula, then in the formula we need the norm of the fundamental vector product. So that's going to be the norm of gamma r cross gamma theta, and that's going to be square root of, we got to square each component and we are going to add, as we know that norm of x comma y comma z is evaluated as square of x plus square of y plus square of z and everything inside the square root. So applying this here, we get 4r raised to 4 cos square theta plus 4r raised to 4 sine square theta and plus r square. So as we can see that the first and the second term have the identity sine square plus cos square, and 4r raised to 4 could be factored out. So this reduces to 4r raised to 4 plus r square. We can also factor out an r square, and that will go out of the square root as r. So we are left out with 4r square plus 1. So that's the norm of the normal or the fundamental vector product. Now we also need the function applied on gamma of r theta. So if you have a look at the function maps xyz to x squared plus y squared. So that means if I talk about f of gamma r theta, then this is going to be f of r cos theta, r sin theta, and 2 minus r square. So if you're wondering how this came, then we have gamma of r theta right over here. So now applying f, so f maps xyz to x square plus y square. So this is what x is. So we got to square x r cos theta, and then we also got to square y. And if you simplify, this reduces to only r square. So thus we have the function, and we also have the norm of the normal. So let's move on to the last part. So the surface integral of f over s is going to be the double integration of f applied on gamma, and that we have got over here as r square multiplied by the norm of the normal, and the norm of the normal is this. So that's r square root of 4 r square plus 1, and then you will have your variables dr d theta, or you could also have the order to be d theta dr. So if I happen to choose this, then the limits of r we have stated over here. The limits of r is from 0 up to root 2, while the limits of theta are from 0 to 2 pi. Now it's a simple double variable integration, and that I will leave it up to you. So in the next video, I am going to take you through surface integrals of vector field and also a number of applications of that. If possible, we'll try and cover up Stokes and Gauss theorem as well. Thank you so much for watching till here, and do like this video if it helps you really. Also subscribe to my channel and share it with your friends who are preparing for surface integrals. Thank you so much.